Welcome to the end of cycle one. So you've finished the first week, and I hope that that went well for you, and I hope that you're enjoying reading Mathematics for the Non-Mathematician. Well, in today's video, we'll be doing a little bit of a review, and I'll also be highlighting and emphasizing a few things which you need to keep in mind. So first, we're actually going to talk about note-taking. By this point, you should have quite a few notes in your journal. You should have all kinds of observations, thoughts, questions, which have occurred to you as you've been reading, and you should have jotted them down in your journal. Now, you should have observed by this point that basically your journal is meant to be something like a running commentary on the reading. That's how it's supposed to work. And if this isn't something that comes naturally for you, then you're going to need to make an extra effort to learn to do this and to make it a habit. So if you're prone to forget these kinds of things, then you'll want to make a note for yourself and maybe stick it in your book so that you will remember to journal as you read. Now, when I say that you need to journal as you read, I should probably explain exactly what that looks like. There are two ways of doing this. The first way is to simply read the material with the pencil in hand. And whenever you come across something interesting, something which you would like to return to later, make a mark in the book with your pencil so that you can return to it. So you can either underline it, or my favorite technique is actually just to make a little vertical line in the margin to tell me where the sentence is. Or if it's a really big passage, I'll make like a little bracket to show where the passage begins, then a little bracket at the bottom to show where the passage ends, so that I'm not making all kinds of marks and cluttering up the reading space on the page. But however you do it, whether it's highlighting or underlining or any of the techniques I've mentioned, it doesn't really matter. The important thing is to note those things which you think are important and interesting. Then, after you finish the reading, you need to return to those passages, pull out your journal, and write your thoughts on those passages, whether they're questions, whether they are insights, something that you finally recognized or realized, or understood for the first time. Write that down. Or even if it's just wanting to record an idea that appeared that you thought was interesting and worthy of further consideration. Those are all the kinds of things you should be writing down. Now that's one method. The other method is to actually interrupt your reading as you're reading whenever you come across a passage like this. So this might be better for those of you who really don't like to write in your books. Then you can read and have your journal open next to you as you're reading. And then whenever you come across something, you can make a note. You can say it's in this paragraph on this page, and this is what it is. And so basically what you'll be doing is making an index for yourself. In either method, both methods really are a form of indexing, where you find interesting things in the book and you make a note about it, and you'll also want to include just a little note about how to find it again in case you ever want to return to those passages and actually read those passages rather than your notes on the passage. So even if you're not writing in the book, make sure you have your journal open next to you so that as these thoughts occur, or as these questions arise, you can write them down immediately and not lose them. And if you do this diligently, at the end of the year, you should have a lot of thoughts, a lot of questions, a few answers here and there, which is good, some insights, observations, all these things in your journal to represent your reading. And not just your reading, but it'll also be a mark of how well and how thoroughly and how carefully you've read. So I encourage you again, keep doing this. I'm not always going to be reminding you to do it. So in fact, most of the time I won't remind you. So it needs to become a habit. And the sooner it becomes habitual, the better. So work on that this next week as you continue to go through the guidebook and into cycle 2. Now, the other thing that we need to discuss before we talk about some of the reading that you've done is the essay. So you've started the essay by this point, you've begun the outline, and maybe that was a surprise to you to see that we have essays in a mathematics course, but it really shouldn't surprise you. Mathematicians have been writing about mathematics for as long as there has been mathematics. And so you'll be writing some notes on the history of mathematics, which is not necessarily a mathematical treatise. It's a little bit easier, of course, but it's really good practice. Mathematicians care just as much for beauty in their essays as they do in their proofs and theorems and whatnot. As I've said before in the guidebook, and I'll keep saying, mathematics is really a discipline of beauty. And that beauty should extend to all aspects of math. It's an elegant thing, and so the essays we write should be elegant as well. So keep working on that essay, and I've got written into the guidebook to help you keep working on it. But pay attention to that. Put in the effort that it requires, because you can learn quite a bit from writing these kinds of essays. So put in the effort, put them to good use, benefit from it. So that was the main thing I wanted to talk about, sort of by way of review. But I do also now want to discuss some of the reading. So we've talked about some of the technical stuff. Let's talk about the reading. So today, or I should say this week, we've been reading the history of mathematics, essentially, as well as some of the characteristics of Greek mathematics. Now, the history of math, as you've seen, is absolutely fascinating. It spans centuries, it spans nations, different nationalities, or I should say different nations. People in different nations have contributed to mathematics tremendously. Even countries who are political enemies have been unified in one sense under the banner of mathematics, just from the fact that so many different nations have contributed to mathematics over the centuries. And the mathematicians themselves led fascinating lives, and we won't really get to see that this first year, primarily because we know so little about the Greek mathematicians. And that's really where we're starting. We're starting with Greece, right? Klein makes this pretty clear. Even has a whole chapter dedicated to the Greeks, right? Because the Greeks really are the beginning point of mathematics. Now, the Greeks learned everything they did about mathematics from the Egyptians and the Babylonians, but one of the things that the Greeks loved to do was absorb the best things from other cultures and then improve on them. And they did that for sure with mathematics. They absorbed the skills, the mathematical skills and techniques developed by the Egyptians, Babylonians, and reduced them to a science, reduced them to a discipline. So they took the tools, which in the hands of the Babylonians and the Egyptians were mere tools, something like hammers and saws, because they were used to do very practical things like calculate taxes, measure land areas. And to the Greeks, these became no longer hammers and saws, but something we might say more like musical instruments, if we want to use that analogy. Because the Greeks took these things and they turned them from their practical use to a very impractical use. And in fact, the Greeks looked so poorly on the practical use of mathematics that no Greek man who was a citizen, no Greek citizen, would ever stoop to the level of using mathematics to do anything as mundane as calculating taxes, land areas, prices of things, counting money. Those were tasks which were so menial and beneath them that they actually gave them to the slaves. So the slaves were the ones who were doing the practical math, but the Greek citizens who were interested in mathematics pursued very impractical math. Now, they would have argued that their mathematics was more practical, as we'll see some later on this year. But basically the reasoning went like this. If we use mathematics to do certain things, practical things, we're using mathematics to tell us something about the material world, right? If we use mathematics to calculate how much, wheat so-and-so owes so-and-so, well, then we're applying mathematics to the material world. And as you've seen from the reading, the Greeks understood that the material world is constantly changing, and they saw this as a problem because they wanted to say that the things which were ultimately true were things which were unchanging, universal principles that never changed. The problem with the material world is that it's always changing. Everything in the material world is in a state of flux or a state of change, right? This is why we are always having to clean our houses, because they become untidy, they get dirty, things change, right? Even if you were to decide, you know what, we're not going to dirty the house, we're just going to leave it and not even live in it, and that way it'll stay clean. Well, you know that doesn't work, right? The house will begin to fall apart if it's not maintained. Animals will get in, it'll still become a mess anyway. And so the Greeks knew everything in the material world was constantly changing. And so in one sense, we can't know anything about the material world. Or to put it another way, the stuff that we know about the material world is not knowledge on the same level as knowledge we have about unchanging universal things. So the truths of mathematics are unchanging and universal truths, and so they are higher truths. And so the Greeks then weren't interested in the practical applications of math because they thought, well, just because you can count beans or something, that's not all that exciting. It may be useful for life, but it's not going to tell me the things which are ultimately true about the nature of reality and the nature of the universe. And that's what they wanted to know. They were interested in ultimate reality. And they believed that mathematics told us about, or tells us about, ultimate reality because it reveals a world to us which is accessible only through reason. And it's purely abstract, which means that the problems that plague the material world, such as change, right? Things in the material world can be lost, they can be destroyed, new things pop up. Those problems don't plague the realm of reason. Everything in mathematics can be proved, and it can be proved beyond a shadow of a doubt. Or at least that was the Greeks' dream, was to be able to have a discipline where everything was perfectly certain, everything was always true. So a realm of perfect harmony and absolute truth. And so to the Greeks, going back to this idea of practical versus impractical math, the Greeks would have said, well, no, the really impractical math is the math that we let our slaves do because that's just the day-to-day financial stuff. which is not elevating to the soul. The really practical mathematics is the mathematics that doesn't apply to day-to-day life, because that's the mathematics which speaks to the soul and elevates the soul by teaching us what is universally and absolutely true. And by dwelling on the universal truths, the absolute truths, these are the things which are going to nourish the soul. And that's far more important than bodily nourishment. So that is essentially, to recap, what you've read in Klein with why mathematics begins with the Greeks, because they're the first ones to approach mathematics with anything like that attitude. Another thing I should point out as well, actually, if you have your copy of Mathematics for the Non-Mathematician handy, you may want to follow me to this passage, because I'm going to read it and make a few comments on it. Let's see, it's on page, there he is, 210. Section 210, it's on page 27. It's that very first paragraph. I'll read the whole thing. You can read along with me. He says, one final point about mathematics is implicit in what we have said. We have spoken of problems which give rise to mathematics, of cultures which emphasized some directions of thinking as opposed to others, and of branches of mathematics, as though all these forces and activities were as impersonal as the force of gravitation. But thinking and ideas are conveyed by people. Mathematics is a human creation. Although most Greeks did believe that mathematics existed independently of human beings, as the planets and the mountains seem to, and that all that human beings do is discover more and more of the structure, the prevalent belief today is that mathematics is entirely a human product. So I want to pause on that idea, because he does say that, well, today we think this way and the Greeks thought the other way, and that's an important distinction to make. And you'll see this this coming week as you begin to read Nicomachus' Introduction to Arithmetic. One of the things you'll see Nicomachus mention over and over again, especially if you know to look for it, is his belief that mathematics is the product of the divine nature, or the divine mind, or was placed in the world by, as he calls it, the world-creating God. To put it another way, Nicomachus believes that mathematics is woven into the fabric of the universe. And when we discover things about mathematics, they're true discoveries. We haven't invented them. Mathematics is not a language we invent. It's a language we've discovered. Today, however, mathematics is often spoken of as a language, right? And languages, of course, are human products in some sense, because you can make up new words, right? Languages change over time. For instance, even though we've all seen, Bible movies where all the characters have British accents, we know Jesus didn't really have a British accent, right? So languages change over time. Languages change into each other. No one speaks Latin anymore. Latin has become a whole host of Romance languages. So in that sense, language is a human creation. But there's another sense in which language, as well as mathematics, is not a human creation. And there's a sense in which it is. And I have to explain this. When the Greeks said that mathematics was something that they discovered about the world, that's true in the sense that the world does obey mathematical principles and mathematical laws. If this weren't true, physics could not exist as a discipline, right? Or at least I should say modern physics. Modern physics is primarily concerned with the mathematical modeling, for instance, of natural phenomena. But that wouldn't be able to exist. You couldn't have that if there wasn't some kind of a genuine correspondence between the way that things are in the world and math. And so we can say that because there's a correspondence, there really is math in the universe, right? It really is there. However, at the same time, it is something that math is sort of something that we say about the universe to describe it. So math is true. It describes the universe correctly, we might say, right? But at the same time, it is something we have said about it. And in that sense, it's a human creation. I'll put it a different way, which may clarify this even more. Mathematics, because it's abstract, because it is a purely rational discipline, it's essentially telling us something about the way that our minds work. In other words, mathematics, in one sense, is an exploration into rationality itself. Just like language, in one sense, is the same thing, because there are certain rules of language that all languages follow. One of the most principal rules is that you have to have a subject to talk about. If there's no subject in the sentence, you don't have a sentence, right? And all languages adhere to this fundamental principle, because it's not just a principle of language, it's a principle of thought. Now, this doesn't mean that grammatically you have to express the subject every time, but it means that even if the subject is not expressed grammatically, it's still present through implication, right? There's always a subject implied, because if there's nothing, well, I'll put it this way, if there's no subject about which you can predicate something, you can't predicate anything. Or to put it another way, the subject of a sentence is what you're saying. Or I should say, what you're saying in the sentence is you're saying about that subject, right? So if I say, for instance, the dog runs quickly. The subject, the dog, is what I'm talking about. And I have to predicate something of the dog for there to really be a sentence. So then I say something about the dog, right? Well, it's running quickly. But if I don't have a subject, nothing else makes sense. If I just say is running quickly, there's nothing there that makes any kind of rational sense in any language, because it's not a complete thought. And so it's just a fragment of information, but it's a fragment of information that's not tied to anything, which renders it meaningless, right? If you just see a random word that's not tied to anything, it's meaningless, right? It'd be like, walking down the street and then picking up a piece of paper that had a single word written on it. Let's just say the paper said Dave. Now, Dave could be a subject, right? But it's not a complete thought. You want to know, well, why is Dave written on this paper? What's supposed to be said about Dave? Or if you just picked up a piece of paper that happened to be floating by in the wind, and the sheet of paper just said running, or is running, or was running. It doesn't matter. It's meaningless, right? Because it's not being said about anything. Similarly, mathematics expresses something, but it expresses true thoughts. Just like language can only properly express thoughts, mathematics does the same thing. To put it in hopefully clearer terms, all languages work and communicate because they follow the same principle of thought. In other words, all languages are rational. Regardless of the grammatical structure of the language, each language has to follow the same basic principles of the rules of thought. Mathematics follows those same rules, essentially. Not exactly the same grammatical rules, you understand, but it also follows rules of thought. And so in that sense, just like we can say that languages are human constructions, right? You can invent words, you can make up nonsense sentences, although they are nonsense and so they're meaningless. But you can play with language, right? You can play with mathematics in the same way. And mathematics, and you can create new words essentially in mathematics. But when you do this, you may be creating something. And so it may be a human creation, but here's the thing. If it makes sense mathematically, it's not because you've invented a new rule of thought. If it makes sense mathematically, it's because you've uncovered a rule of thought that was already there. We can't change the way rationality works. We can discover new ways to say things. We can discover new things to say. But to come up with a completely new law for thought, that's impossible. So that's going to be it from me today. I hope that that's been interesting. I hope that that sparked all kinds of new ideas. So think about these things. It's always worth taking time to think more deeply about what you're reading. So just like I said in the introduction video, I encourage you to keep doing that. Whenever you have time, make time to just sit and think about what all this means. Mathematics is not just about manipulating numbers, and geometry is, of course, is part of mathematics, but geometry isn't just, about making funny shapes and measuring them. There's much, much more going on than just that. And what's going on, if we pay attention, can teach us a lot, not just about the world around us and the way that God has structured the world, but it can even teach us about ourselves and the way that our minds work. So have a great rest of your week. I hope that you enjoy Cycle 2. Lots more interesting stuff coming up, and we'll see you next time. Goodbye.